Hello everyone, welcome to the video lecture. Today I am going to talk about an introductory review of some very basic concepts in quantum mechanics. This includes the unit 1 of the paper PHHT 502 Quantum Mechanics 1. So, the first part that I am going to talk about is a bit of introduction and some historical background before I actually enter into the topic. Now, the most important concept that quantum mechanics starts with is a discussion about waves and particles. Now, you know, waves and particles have totally very different kinds of behavior. By nature, particles are localized. They have a well-defined position or location, if you will. Their trajectories are known, well-defined, and can be calculated with infinite amount of precision, classically speaking. They are governed by the dynamics of Newtonian mechanics, and you can measure its mass, energy, velocity, and all other dynamical parameters. As opposed to this, and totally contrary to this kind of a behavior, there are waves which by nature have got a spread. They are not localized, and therefore waves and particles are not really comparable with respect to their properties. And the question that begins all of this is the classic debate between Newton and Huygens. Whereas Newton claimed that light is a series of particles or corpuscles that he called it as, Huygens believed that light behaves like a wave. Between Newton's corpuscular theory and Huygens' wave theory, eventually we realized that light actually behaves like a wave. The puzzle of light. Finally, when Maxwell wrote down his famous set of equations, we realized that light actually is an electromagnetic wave. You can define a wavelength, you can define its frequency, and its velocity is frequency times its wavelength. Once we established light as a wave, we can explore the properties of light as a wave and compare it with that of well-known and well-defined particle behavior. Look at this particular slide, the phenomenon of reflection, refraction. Both particles as well as waves show this property, whereas the well-known phenomenon of interference, which came from Young's double slit experiment, is something that only waves show. Particles do not show interference pattern. Similarly, diffraction, the property of waves to bend around obstacles and corners. This is a wave behavior and particles do not show this. Similarly, polarization. Polarization is also an exclusive wave phenomenon. Particles do not show the property of polarization. So, in this sense, given a particular entity or a system, you could classify it as either a wave or as a particle depending on which of these properties is predominant. Let's look at the double slit experiment because this is going to be the foundation of what we are going to discuss. As you can see in this particular slide, I have a gun which I assume is firing bullets at a constant rate uniformly, and it is firing a stream of bullets, and there are two slits in front of it. When one slit is open and the other is closed, most of the bullets would pass through that slit. You close that particular slit and open the other one, most of the bullets would pass through the other slit. So now when you calculate the distribution of the bullets fired from the source, that is the gun, you would see a behavior like this. When both the slits are open, 50% of them would pass through slit 1, 50% of them would pass through slit 2, and eventually you are left with a 50-50 kind of a distribution. If you say that intensity is something like a measure of the total number of particles, then you would get an intensity distribution like this, where P sub 1 is the intensity distribution for the bullets passing through slit 1 and P sub 2 is the intensity distribution for bullets passing through slit 2. And when both the slits are open, the intensities simply add up. And this is a particular property that all particles exhibit. So, bullets here are particle-like behavior that is shown. Now, instead of using a gun, which is a source of bullets, particles, if I use a source of a wave like a light source or something, which is a classic interference experiment, the Young's double slit experiment, you would see that when both the slits are open, the intensity gets redistributed. You can see in the graph that there is a variation in the overall intensity. Unlike particles, when waves interfere, they show a redistribution of energy. So, this phenomenon is exclusive to waves, and interference proves that light is a wave. This acts as a point of departure for particle and wave behavior for us. As you can see in this diagram, an incident plane wave, after it passes through both the slits, the secondary and tertiary wavelets and wavefronts interfere with one another, and depending upon whether the crests or the troughs or crest and trough match with one another, the eventual superposition gives you alternate bright and dark fringes. These are called the interference fringes. And this phenomenon of interference is not shown by particles. So, that is why there is a very exclusive kind of a pattern to particles which show bullet-like behavior, and there is a very exclusive behavior for waves which shows a interference pattern. So, with this background, I would like to look into what happens when you enter the next phase in our analysis. So, this is a very typical ripple pattern. As you can see, the ripples show a wave-like behavior, unlike particles which do not show an interference pattern. At this point, let me just take a pause and we'll call it the end of part 1. In the next part, I'll continue with the particular properties that I was talking about with respect to interference. Thank you.